So other types of regression. So up at the top it says, in the last 2 lessons, we fit bivariate data sets with lines of best fit. So we did the scatter plots, then we drew in the line of best fit, then we used our calculator to draw in the line of best fit and do the work for us. Come up with the slope, come up with the y-intercept, and we went from there. Sometimes, though, linear models are not the best choice. There are other types of regression models out there. It says we can fit data with all sorts of curves. The most common are linear, okay, which we've spent a lot of time with. We also have exponential, and then we'll also talk about quadratic. There are other types, but those are the only 3 that we'll talk about in algebra. Before we look at the exponential and quadratic regression, refresh your brain. Exponential looks like that. Okay, we've got growth, the first one, decay in this one, and then quadratics are parabolas. Okay, opening up or opening down. So we can come up with the curve of best fit. It's not always the line of best fit. Depends on the data that you're given. So I take a look at exercise 1 for each scatter plot shown below. Oh, these are the answers. Oh my goodness. All right, I gotta pause and go back to a different. Okay, now that we don't have the answer key up. So for each scatter plot shown below, determine if it is best fit as linear, exponential, or quadratic function. Draw a curve of best fit depending on your choice. So go ahead and draw in what you think would be best. Linear, exponential, quadratic. All right, so that first one kind of got that curve to it, so that one would be exponential. We've got quadratic, exponential, that one's a decay one. I would say that one would be linear, okay, with a negative correlation. We've got linear with a positive correlation or a positive slope, and then we also have another quadratic that comes up. Okay, pretty simple. So it says our calculators could produce the equations of exponentials and quadratics, just like it did with our linear. Okay, so we can do the same things that we did with linear with these other 2. So it says biologists are modeling the number of flu cases as it spreads around a particular city. The total number of cases, Y, was recorded on each day, X. So our days are X, our cases of the flu are Y. After the total first reached 16. So they started recording data when there were 16 cases of the flu. Okay? The data for the first week is shown in the table. So we're going to take that and enter it into our list and spreadsheets, and then we're going to go through all the same steps that we would for linear, but instead of picking the y equals mx plus b, we're going to find the exponential regression equation that looks like this. And then we're going to make sure that we round to near 100. So go ahead, enter that data in, get your scatter plot, and then we're going to do menu analyze, but we're going to pick exponential. So once you have that, okay, it does look kind of linear. It does look kind of linear. But the one thing it said back here, it says exponential regression. They're telling you which one that they want you to use. But think about the context of this problem too. They're talking about the flu spreading. And when you're talking about bacteria growing, that never happens in a linear fashion. Okay, bacteria growing, mold growing, anything like that occurs in an exponential fashion. Okay? So once we have this, then we're going to go to our menu analyze regression, but now I want to pick number 8, exponential. Okay, because it's exponential, and then it is drawn in our
line or our curve of best fit, and it has given us the equation, and they want us to round those parameters to the nearest hundredth. Okay. So the y-intercept in that growth, they want it to the nearest hundredth.
So y is equal to 15.92 times 1.12 to the x.
Good with that? Now they're going to have you use that equation. So it says, based on your regression equation,
How many total cases of the flu will there be after 2 weeks?
2 weeks. So now they're asking us,
Okay, I want to find out the y if I know the x. The x in days would be what for 2 weeks? 14, yeah. So 15.92 times 1.12 to the second power. Go right to your calculator. Who's got it? How many cases? Anybody? Okay, so we're talking about people here, so we're going to say 78 cases of the flu. Right? According to your model, by what percent are the flu cases increasing on a daily basis? So go back to what we know about linear exponential growth. Okay, that's our y-intercept, or where we begin. Does that fit with our data? When did they start recording how many flu cases were there? When there were 16 cases. Does that come pretty darn close to our model? Sure does. Now, when you remember about exponential growth, it's always 1 plus the rate. So what is the rate? 12%. Okay. So they increase it 12% per day, the number of cases of the flu. It says hospital officials will declare an emergency when the total number of cases exceeds 200. Okay? Exceeds 200. So when there's all of a sudden 201 cases of the flu, that's when they declare an emergency. On what day will they need to declare this emergency? On what day? So already in part B, on, oh, that's got to be 14. Correct me on that. Okay. So on the 14th day, there's 78 cases. So now just play around with the calculator and type in, I don't know, 16 days, 17 days. See what you get. Dylan, you got the answer already? And because on the 22nd day, okay, if you did to the 22nd, you end up with 193 cases. So then I would go to that, because we're almost there, to the 23rd day, and you end up with 216 cases. So on the 23rd day is when they would declare that an emergency. So it says, so really, regression, as mysterious as it may be, is all about finding the best version of whatever curve we think fits the data best. So if we think it's linear, we go with linear regression. If it looks more exponential, we go with that. And then I think this one does quadratic, if my memory serves me correctly. So let's look at this third example. This is the cost per widget produced by a factory generally drops as more are produced, but then starts to rise again due to overtime costs. So think about those words there, okay? And a widget is just anything, okay? Anything that could be produced. The cost per widget by a factory generally drops as more are produced, but then starts to rise again due to overtime costs and wear and tear on the equipment. So think about those words then take a look at our data. It says quality control engineers recorded the data cost per widget compared to the number of widgets produced. So the number of widgets X, the cost on Y. So kind of take a look and see what's happening with the data. Why should a quadratic model be considered for this data set as opposed to linear or exponential? Just think about the words that we underlined there, and then take a look at what's happening with the data. Okay, the X's are definitely increasing, right? And then look what's happening to the Y's. They're decreasing, but then they start to go back up. So now take a look at the scatter plot. It says use your calculator to create a scatter plot of this data to verify it's quadratic in nature. Okay. So we could say the X's, okay, increase. Okay, they consistently increase our X's. But more importantly, what's happening with the Y's? The Y's decrease, then increase. So when you take a look at your scatter plot, you should start to see that that's quadratic.
So your scatter plot should look like that. Okay, if I were to draw in, okay, that curve, you can definitely see that it is quadratic in nature.
Okay? All right, so let's hop over to the next lesson, lesson 9. Okay?
All right, so quantifying predictability. Okay, so putting a quantity or a number
to how predictable our information is. Quantifying, putting a number to how predictable something is. So it says, in the last few lessons, we have worked with generating lines and curves of best fit for bivariate data, 2 variables. In every circumstance, though, the data did not fall on a straight line or a perfect curve. None of the data that we looked at, when we put it in the scatter plot, was exactly in a perfect straight line, okay, or exactly as an exponential or quadratic equation. It was close. Okay, it was close. So it says we've never answered the question of how well specifically a linear model does in predicting the correlation between the 2 variables. Okay? So it says that I will explain where the R value is on our calculator. Remember when we go into our list and spreadsheets and we don't want to look at the graph or the picture of something, and we go to menu, analyze, 2 variable statistics, and then all of our stuff appears on our list and spreadsheets. We get the title, we've got the mean, we've got the standard deviation. It's going to appear there. Okay, it's called the correlation coefficient, and its notation is R. Don't know why they picked R, but it is. Okay, so that is the correlation coefficient, and we'll see that in just a minute. Okay. So it says in the following exercises, 4 data sets with equal X values. So all the X values in all 4, right, are the same. Okay, and they have positive correlations. Positive correlations means it's got a positive slope to it. Okay? As one increases, the other increases. For each, enter the data, observe the scatter plot, and record the R value, known as the correlation coefficient, for a linear fit, okay, to the nearest 1,000. All right, so let's just deal with A right now. So everybody go ahead and enter A into your list and spreadsheet.
Again. Okay, so once we've got that entered, let's look at the scatter plot. Okay? It looks pretty darn close to linear, doesn't it?
Yeah.
And what are the directions asked us? It says for each, enter the data, observe the scatter plot, and record the R value known as the correlation coefficient for a linear fit. Okay, for a linear fit. That certainly does look very linear to me. So I want to go and I want to find the R value. So they're not asking us to draw in the line of best fit right now. So go back to your 1.1 page, meaning your data and statistics page, or your list and spreadsheets, I should say. So now we're going to go to Menu, Statistics, Stat Calculations, 2 variable statistics, because that's what we have. We called our first list X, we called our second list Y, and we click OK. Okay, so now we got all this good information. So scroll down your title column till you find R. Okay, you got to kind of go down to the bottom there till you find R. When you look next to that, what number do we get? 0.99898. That's pretty darn close to what? 1. Okay? And what that does is that verifies to us what we projected back here. We said that is pretty darn close to perfect. Okay? So when your R value is really close to 1 or really close to -1, it is pretty darn close to a perfect fit, perfect line in this case. Okay? So they want us to write down that our R value nearest 1,000, okay, with that, and we would characterize that as a very good fit. The closer that number is to 1, the closer it is to perfect in a positive direction, or the closer our R value is to -1, the closer it is to perfect in the negative direction. Okay? So the further we get away from 1, meaning closer to 0, that would mean really bad fit going on there. Okay, it's a really bad fit. So let's go ahead and do B, C, and D. Do all 3 of those, and then we'll come back. Okay, who's got B? Okay, B. Brian, what'd you get for the R value?
0.93.
0.930 to the nearest 1,000? 0.930. Is that as good as A?
No.
Okay. We would say that that's an okay. Okay, that's an okay fit. And when you looked at, okay, those of you that did B, when you looked at your scatter plot, it was probably pretty good. Right? Pretty close to perfect, but not quite like A. Those of you that did C, and what'd you get for the R value? 0.776. Okay. Clearly away from B, not as good as B, and certainly not as good as A. And then when you looked at the scatter plot, it was even more scattered, right? So I would say that that's a poor fit. Okay, it was very scattered when you looked at it. Okay, and then I did D along with the right side of the room, and that's what D looks like. Okay. Is there any kind of fit going on with that?
Yes. What is that?
Not really. Okay. Especially when they're talking about what did the directions say? The directions said linear, my friend. Okay? Linear fit. So we would say, well, the R value was that. That's really far away from 1. Okay? Positive 1. And almost no fit at all. So So it says, how does the correlation coefficient quantify the fit of a positive correlation? Okay, so how does it put a number to that? So the better the linear fit, meaning the closer it is to a straight line, okay, the closer the R value is to what? Yeah, closer. The R value is to +1 because this one said just about a positive correlation. Well, what about as it gets further away from 1? Okay, the poorer the linear fit, the closer the value is to what number? 0. Okay. So I'm going to write that down here. Closer the R value is to 0. Okay. All right, so exercise 3, it says the following data is that of two variables that have a negative correlation. Okay, negative correlation. So if it's a negative correlation and it's linear, it's going to be going downhill. Okay, from left to right. It says enter the data, produce a scatter plot, record the R value. How is the negative correlation reflected in the R value? So to save some time here, I'm going to give you the R value. The R value is -0.945. So you guys have not looked at the scatter plot, okay, because I kind of sped us through that one. If the R value is -0.945, what could you say about the fit of this line? Okay, they're all linear right now. Okay, it's pretty darn close to, would we say it's good? Would we say it's perfect? What would we say?
Pretty good.
It's pretty good. Okay. It has a negative value. Pretty close to -1, right? So we'd say it's a pretty good fit. Okay, it's a good fit. It's not perfect. If it were -0.999, that would be pretty darn close to perfect. Okay? All right. Let's go ahead and flip to the next page. I don't think we need to do all of these on the next page, but we'll take a look. So we got a multiple choice question in 4. It says, given the scatter plot, which R value would most likely represent the correlation between the two variables? Explain your choice. So what is this doing? Which choices could I eliminate without too much thinking, maybe? Okay? Not exact. 4 because it's negative. It's definitely not negative. Okay? Yeah. Number 2 we can eliminate because it's pretty good. Okay? So that's 0.88. Awesome. Which of the following scatter plots would have a correlation coefficient closest to -1? Okay. 4. Downhill, pretty good. Okay, pretty close to, what about number 3? What would that be close to? Well, what's nothing then? Yeah, it'd be closer to 0. Okay. All right, guys, we're good.